assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
For this problem, we are told that we have a vertical spring which stretches a distance of 9.6 centimeters or 0.096 meters after a 1.3 kilogram block is attached to it. And we're asked to find a variety of things, but the first thing we're asked to find is the spring constant. So we are going to use the equation force equals K times X. And in this case, because it is the force that's acting on this system is the force of gravity, we're actually going to replace our F with mass times gravity equals K times X. And solving for K, we would change this equation to K equals mass times gravity divided by X. And we can now substitute in our known values, which we have as the mass is 1.3 kilograms, gravity is obviously 9.8 meters per second squared, and our displacement is 0.096 meters. So we end up with a spring constant that equals 1.33 times 10 to the second newtons per meter. Next, we are told that that the spring is pulled down and displaced an additional 5 centimeters and released. So it was at rest. It is now oscillating with simple harmonic motion, and we are asked to find the period of this motion, the frequency, the maximum amplitude, and the maximum velocity. So to find our period, we're going to use the equation T equals 2 pi over omega, and omega also equals the square root of our spring constant divided by our mass. So we can take this and replace the omega in this equation, which will give us the equation T equals 2 pi times the square root of mass divided by our spring constant. And now we can plug in our values, so we'll end up with 2 pi times the square root of 1.3 kilograms divided by 1.33 times 10 to the second newtons per meter, giving us a period of 0.62 seconds. We're then asked to find our frequency, which is easy because we can just use the equation. Frequency is 1 divided by the period. So we have 1 divided by 0.62 seconds, and we get that the frequency is 1.6 hertz. So now to find the amplitude, we have to think about the scenario that we're working with here. At first, we started with a block that had a displacement. When the block was attached, the spring stretched 9.6 centimeters. Then the block was pulled down, and it was pulled down a total of 5 centimeters and let go, and that's when it started to oscillate back and forth. Now, since it's simple harmonic and our amplitude is based from the position of equilibrium, which is where the block was before it was pulled down, we can say that our maximum amplitude is actually going to be that 5.0 centimeters, because that is how far the block was pulled down before it started oscillating. The final part of this question asks us to find the maximum velocity that the block will be moving. And so we have a couple of things we have to think about. So first, the block was at rest, then it was pulled down, and until it was let go and started to oscillate, it had a velocity of 0, and it had a particular potential energy. And then when it was let loose, the block started to move upwards and hit its maximum velocity when the block passes through the equilibrium point, because after that, since it's going against gravity, the velocity is going to start to decrease. So to find the initial potential energy, we're going to call this U I. We're going to take the equation negative mg x plus 1 half kx I squared, that should be xi. And our xi is our initial position. So now initially, put this over here, initially, before it was pulled down, the block was at 9.6 centimeters, but then it was pulled an additional 5 centimeters. So our initial position before the oscillations began is going to be 14.6 centimeters, or 0.146 meters. And so this is the value we're going to be using in here in this equation, because that is the initial position. So solving for ui, we are going to have ui equals negative 1.3 kilograms times 9.8 meters per second squared times 0.146 meters plus 1 half 1.33 Newton per meter times 0.146 meters squared. And we get our initial potential energy ends up being negative 0.44 joules. And we're going to do the same thing with the potential energy left once the block hits our point of equilibrium. So again, we're going to do negative mg xf this time, which is going to be our point of equilibrium, plus 1 half kxf squared. So we will have our final potential energy will be negative 1.3 times 9.8 meters per second squared times 0.096 meters, because that's where the block reaches equilibrium, plus 1 half times 1.33 newtons per meter times 0.096 meters squared. And we get that our final potential energy is going to equal negative 0.61 joules. Now energy is conserved, so however much energy there is, initial potential energy must be equal to the final potential and plus the kinetic energy. So our initial energy has to be equal to our final potential plus our kinetic, which is 1 half mv squared. And so you can see now we're going to be able to solve for our velocity. So if we rearrange this equation to solve for velocity, we end up with velocity is going to be equal to the square root of 2 times ui minus uf divided by m. And substituting in our values, so we have our values over here, we're going to have the square root of 2 times negative 4.44 joules minus negative 0.61 joules divided by 1.3 kilograms. and that is going to give us a final velocity of 0.51 meters per second.